All right. What isotope do we use?
Gold, 198.
All right, Tyler State. Gold 198. All right, here we go. So, did I do this with you yesterday? Oh, all right. Write this in your notes. You're going to draw little circles. You guys saw me do this in lab, correct?
Yeah.
All right, so all these red circles here represent one atom. Each red circle is one atom of gold 198. All right, so we have, I'll do it over here. AU 198 over 79. What type of decay is it? Alpha? I mean, is it beta or positive?
Beta.
Beta. 0, -1 E plus 198 over 80 Hg. All right. Now, somewhere in the vicinity of these notes, it doesn't have to be right next to it like I'm going to do it. It could be underneath it. But I need you to set up this chart, which is how I teach half-life calculations. All right? So, we got mass, time, and half-life. This chart is going to be very useful to most of you. By the end of class, if you fully understand half-life and you can do these problems we're going to be going over without using the chart, that's fine. But you're going to have to show me how to, basically you're going to have to show work somehow on the homework. And I guess Fred's probably the only one that knows what I'm talking about right now because the rest of you haven't looked at it yet. But I'm going to give you about 3 sample problems today, maybe more. We'll do as many as we can, showing you how this chart helps you answer Regents level half-life problems. So that's the goal here today. All right. So this mass here is going to be the mass of gold. Now I'm going to add another column here, and this is going to be mercury. Mercury's mass. So I use this one example, and I use the magnets to really help you conceptualize what the heck half-life is. So I'll go through this kind of slow, and then we'll get into practice problems. It'll make more sense when we're done. Right now you're probably like, what's he going to do? What's going on? What's the definition of half-life, Alex?
The time it takes for half
Good. So after one half-life, so eyes up here, after one half-life, half of these atoms will transmutate into mercury. So I'm going to show that using the magnets. Yellow is going to be mercury. Red is our gold. So, what's the chart have to do with anything? Well, here's how we do it. We put 0 here, 0 here. What does that mean? Well, imagine we can stop time. We have a stopwatch, and that stopwatch controls time. Okay? So initially, the stopwatch is off. So right now, we have all the atoms of gold. How many atoms do we have?
16.
16. There's 16. Now, I'm just for simplicity, I'm going to say each one is 1 gram. That's way too big. 1 atom of gold doesn't weigh 1 gram. Okay? But just for simplicity, we're going to say, all right, we have 16 grams of gold initially. Now, since it hasn't started decaying yet, how many grams of mercury do we have?
0.
0. So, now we draw a line underneath. That's like our first column, first row. After, did someone have a hand raised over here? Yeah.
If gold is 79, how does it turn into Hg that's 80?
It ejects an electron from its nucleus. Remember the quark conversation the other day?
If it ejected it, wouldn't it lose?
No,
it?
no, it loses a negative adding a little more.
It loses an electron, which is -1.
Okay.
So therefore, to make up the difference, there has to be another positive proton.
Okay, right.
Does that make sense?
Yes.
Okay. All right, so after one half-life, go to table N. What is the half-life of gold 198?
2.65.
2.65 days?
No, 695.
Oh, 695. All right, I made this too narrow. Give me a second here. Okay. 2.695 days. All right. So, Veronica, we have 16 red circles, 16 red atoms of gold. After one half-life, so we hit our stopwatch, and 2.695 days pass. If we have 16 atoms initially, how many atoms or grams, it's the same answer, do we have remaining? If it's 1 half-life. So if we start with 16 and it goes through a half-life, Alex, read the definition again.
Time for
Half of the atoms.
turn into
Right. So half-life is the time it takes for half of these to turn into this. So again, Veronica, if we have 16 after one half-life, how much do we have? The key is half.
So 8.
8. Very good. We only have 8 grams because half of it has decayed. That's what half-life is. So I'm gonna take random and 8 random particles because in half-life, and I know Mr. Decker explained this in lab, every time a half-life occurs, it's like a coin flip for every single atom. So maybe this one decays, but this one doesn't. This one stays gold. So I'm just gonna pick them randomly. So here's 1, 2, 3. Take one in the middle here. 4, 5. Take this one, 6, 7, and this one, 8. So there's my 8 random particles, or atoms I should say, that have now transmutated into mercury. So how many red ones are left? 8. That's where that comes from. How many grams of mercury do we have? 8, right. After one half-life, it's always 50-50. Always.
If there's a chunk of gold and like half of it changed is into mercury, does the mercury like have bonds with the gold, or is it just like with it?
Good question. Since they're both metals, I would say there would be attractive forces there. But sometimes these things turn into some weird stuff. Like maybe a gas, and it wouldn't stay with it. So that's a good question. Yeah.
Since mercury is a liquid, does that become just liquid?
That's a good question. I don't know, because if you have individual atoms of a liquid, it's not really a liquid yet unless there's more of it that
Yeah.
that makes up a liquid. So I don't
Yeah,
know.
it's
If it's
more
stuck
like
in the middle of gold atoms, I would say no, it wouldn't be a liquid. That's a good question. All right. Next, one more half-life goes. How much time has passed?
5.39.
5.39 days. How'd you get that?
I used a calculator.
Explain what you did with the calculator.
2.695 times 2.
2.695 times 2, or 2.695 plus 2.695. This is really important for everybody sitting here to understand this. And if you all get it and I'm going too slow, don't just deal with me. This is the half-life, and that number never ever changes. Every time it goes through a half-life, it's the same amount of time, every single time. So in this case, it happens to be 2.695. So you always add 2.695. Or multiply that number by 2 will work. However, eyes up here, I want to make sure you're paying attention. Everybody look up here. For the next half-life, you cannot multiply that by 2. You have to add 2.695, because 2.695 is the half-life, not 5.39. So if you add this every time, that's how I explain it. If you add the half-life every time, you'll be safe. Okay, so how many grams of this now decay? Or how many atoms decay now?
4.
4. Because 4 is half of 8. So 1, 2, 3, and 4. So we take 4 away, and now those 4 have turned into mercury. 1, 2, 3, 4. How many grams of mercury do we have now? 12. Good. One more half-life. How much time has passed? 8.085 days. Okay? Adding 2.695 to 5.39, we get 8.085 days. Okay, so you just keep adding the same number over and over, whatever the half-life is. The half-life is from table N, and that's going to be that first time. How much remains? 2 grams remain, because 2 grams decay. So I'll take these 2. 2 grams decay into mercury. Now what's this? 14. Let's do one more. After 4 half-lives,
10.78.
10.78 days, 1 gram remains, and now we have 15 grams of mercury. And here's the crazy part. After one more half-life, that may not change because it's a coin flip. It's all probability. So it isn't set in stone. If it gets down to one little atom, it may actually not change. When you have like millions of atoms, then half of them will change because it's probability. But if you only have one penny, it may not be head. You could flip it 5 times and maybe tails every time. So it's a probability, which is kind of crazy. So sometimes these things get down to one atom and it doesn't necessarily transmutate maybe right away. Yeah.
Will it eventually though?
I'm gonna say yes, but there's probably a math explanation that yes or no. But I'm gonna say yes, eventually it will. And especially it depends, right? If the half-life is 4 billion years or 2 seconds. If it's 2 seconds, it's gonna be, that coin's gonna flip very quickly and it'll eventually change. If it takes
So
4
it just
billion.
keeps going through half-lives until.
Well, time will just go, right? We can't stop time until it changes.
You can
Yeah.
slow down time.
Yeah, well, the faster you move. Have you seen that movie yet?
No.
You have.
Yes.
You're the only one that had. You have to see
Yeah.
it again, and then you and Zeke
Zeke
need to
still
get
has
together
to
and
watch
watch
it.
it. Yeah.
That was literally the same.
Yeah. All right. So this, what I just went through, is everything you need to know about half-life. It's just now let's get into sample problems from the regents. That's going to ask you questions, and I use the chart to answer them. All right. Once you guys get good, with this, you don't need to use the chart, but for today, humor me and use the chart in your notes. So here we go. I'm going to give you a sample question. I'll give you a couple minutes to try and figure it out. If you want to work together, you can do that. Here's the sample question. Write this down. A 100-gram sample of carbon-14 decays for, what is that number? 17,145 years. How many grams, how many grams remain unchanged? What is wrong? Unchanged. So what that means is, and I'm wording it like the regents, is why for me it's a little strangely worded. What this question's asking is, all right, you have 100 grams of carbon-14, and it's giving off radiation for 17,145 years. Well, let's say you could stop time right at that 17,145 year mark. You would have a certain amount of carbon left because not all of it has decayed yet. How much?